Welcome to another deep dive. Today we're digging into something pretty central in AI right now.
Yeah, this whole idea of building AI models that can, handle different kinds of input, like images and text together.
Exactly. For years, the goal has been these general-purpose multimodal models. And the usual way, lately at least, is taking pre-trained vision models, pre-trained language models, and sort of connecting them up.
Wow.
Late fusion, right.
That's the common approach, yeah. But the big question this paper asks is that actually the best way? Is it inherently superior?
Right. Which brings us to the paper, Scaling Laws for Native Multimodal Models.
And what they do is step back and look at what they call native multimodal models, NMMs for short.
Native meaning?
Meaning trained from scratch, right from the beginning, on all the different data types together. No pre-trained separate parts glued on later.
Okay. And they did a huge study, right? Like 457 models.
Yeah, a massive scaling study. Varying architectures, different mixes of training data, really comprehensive.
So, for everyone tuning in, especially if you just have a minute, here's the quick version, the main takeaway.
Go for it.
Okay, so these native models, specifically the early fusion ones, where image and text get processed together right from the start in one unified model without a separate pre-trained vision bit, they're basically not worse than the late fusion approach.
Yeah, no inherent disadvantage found performance-wise.
And actually, early fusion seems better when the models are smaller, it's more efficient to train, uses less compute, less memory, and it's simpler to get running.
Plus, they found that using mixture of experts, or MoEs, gives these early fusion models a really significant boost. It lets different parts of the model specialize.
We'll definitely get into MoEs later. So for our listeners, the AI researchers, the ML engineers trying to keep up.
Which is basically a full-time job these days.
Yeah. This deep dive is about getting you quickly up to speed on this important paper. Beyond just the abstract, we want to understand the core arguments, the evidence.
And some of these findings, especially about early versus late fusion, are genuinely surprising. They challenge what a lot of people, myself included maybe, assumed.
Okay, let's jump into that core comparison then. Early versus late fusion performance. First, maybe just redefine NMMs quickly in this context.
Sure. So native multimodal models, NMMs. In this paper, they're neural nets trained from scratch, simultaneously on images and text. The goal is to output text.
Got it. Trained from the ground up on both.
Not stitching pre-trained bits together.
Okay. And within that NMM idea, what does early fusion look like architecturally?
Early fusion here means the model starts mixing the modalities really, really early. Very few separate parts at the beginning.
Like how early?
Think like maybe just a simple linear layer to turn the image into patches, kind of like text tokens. After that, one single transformer gets everything tossed in together.
So raw text tokens and these image patches all processed by the same core model from layer one.
Pretty much, yeah. No separate vision encoder doing its thing first. No image discretization or anything like that. Very integrated.
Okay, super integrated. Then how does the native late fusion setup differ? Still trained from scratch.
Right, still trained from scratch on both image and text. But in late fusion, the interaction between the image info and the text info is delayed. It happens deeper in the network.
So separate streams initially?
Typically, yes.
Yeah.
You might have a sort of vision pathway and a text pathway processing things independently for a while. Then later on, their representations get combined.
Like the CLIP architecture they mentioned?
Exactly. CLIP is a good example. Distinct vision encoder, distinct text encoder, and then you bring their outputs together.
Okay, architectural difference is clear. Now, the million-dollar question. Performance. What did they find comparing these two when trained natively?
This is the really striking part. When you train both types, early and late fusion, using the same amount of the same total FLOPs, they basically achieve the same validation loss. Performance is on par.
Seriously? The same loss?
Essentially, yes. Look at figure 1 left, figure 2 in the paper. The loss curves track incredibly closely as compute increases.
Wow.
And even the scaling exponents, how fast the loss drops with more compute, they're almost identical. Like L proportional to C to the minus 0.0492 for early and minus 0.0494 for late.
So fundamentally, given enough training compute, neither architecture seems inherently better at the task itself.
That's what the data suggests.
Yeah.
Which, flies in the face of the current trend favoring late fusion.
But I remember you mentioned something about parameters, like how many parameters they need.
Yes. That's the other crucial piece. While the final loss might be similar for the same compute, how they get there is different.
How so?
Early fusion models need fewer parameters to reach that same level of performance compared to late fusion models trained with the same compute budget.
Okay, that's a big deal. Fewer parameters means smaller models, easier deployment, less memory.
Exactly. Figure 1 right shows this trade-off really clearly. Early fusion is more parameter efficient for given compute spend.
Can we quantify that difference a bit more? You mentioned something about the optimal parameter to data ratio.
Right. They looked at the compute optimal balance, knopped over dopped. For early fusion, this ratio scales with compute C as roughly C to the 0.053.
Okay.
But for late fusion, it scales faster, C to the 0.056. Meaning as you scale up your training compute, the optimal late fusion model tends to get proportionally bigger, parameter-wise, than the optimal early fusion model. Late fusion seems to rely more on just adding parameters.
Gotcha. And what about performance, not just at the optimal point, but say at smaller model sizes? Is there a difference there?
Yes, there is. Figure 3 and also Figure 14 in the appendix, they show early fusion actually has a slight edge, performance-wise. Yeah. Especially with smaller models.
Interesting.
That gap does seem to shrink as the models get really big, but certainly at the lower end of the scale, early fusion seems more effective.
So, summary so far. Late fusion isn't inherently superior performance-wise, and early fusion is more parameter efficient, especially for smaller models. Fascinating stuff.
Definitely shifts the perspective.
Okay, let's zoom out a bit and talk about the scaling laws governing these NMMs more broadly.
Right. A big part of the paper is showing that these native multimodal models, both early and late fusion, follow scaling laws, much like we've seen with text-only large language models, the Kaplan and Hoffman papers, Chinchilla, etc.
Meaning performance improves predictably with more compute, more parameters, more data.
Exactly. Loss goes down predictably as you scale up N parameters, D data, and C compute.
But I guess the specific numbers, the exponents in those laws, might be a bit different because of the multimodal data.
Precisely. They found the general form holds, but the exact values depend on things like the type of data, the mix of image and text. Table 3 breaks this down.
So for a typical early fusion model, what did those scaling exponents look like? They used that standard L plus an alpha plus BD beta formula.
Yep. And for their average early fusion results, they got alpha, the parameter scaling exponent, around 0.301, and beta, the data scaling exponent, around 0.335.
How does that compare to, say, Chinchilla? Weren't their exponents slightly different?
They were. Chinchilla reported alpha around 0.339 and beta around 0.285. So the NMM values are in the same ballpark, but maybe suggesting a slightly different balance.
Similar, but maybe NMMs benefit a tiny bit more from data scaling relative to parameter scaling compared to Chinchilla, or is that reading too much into it?
It's close, but yeah, this slightly higher beta for NMMs, 0.335 versus 0.285, might suggest data is marginally more impactful relative to parameters here.
Okay, and this lets them predict the optimal way to scale parameters and data with compute, right? NOPT and DOT.
Exactly. For early fusion, they found NOPT scales roughly as compute to the power of 0.526.
Okay.
And DOPT, the optimal number of tokens, scales compute to the 0.473.
So pretty close exponents, 0.526 and 0.473. Reinforces that idea of scaling parameters and data together as you increase compute.
Mm-hmm. Roughly balanced scaling seems key. They also found DOPT scales with NOPT to the power of about 0.899.
What's the practical takeaway from those NOPT and DOPT scaling numbers for NMMs?
It suggests that for a given compute budget, the ideal native multimodal model might be slightly larger in terms of parameters, NOPT, compared to a language-only model, while perhaps needing slightly less data, DOPT. But again, the main point is that scaling both together is crucial.
And the late fusion models showed similar scaling trends for NOPT and DOPT.
Yeah, figure 2 right in table 3 indicate comparable behavior. The general scaling picture holds for both, even if the exact numbers vary a bit.
It's really valuable to see these predictable laws holding up for multimodal. Take some guesswork out of training. And they tested these predictions.
They did. Figure 7 and table 5 showed their scaling law predictions were really quite accurate. They even predicted the performance of an 8 billion parameter model they'd held out pretty well.
That gives you confidence in the laws. Okay, right. Prediction is great. Let's talk practicalities again. Training efficiency. You hinted early fusion was better here.
Yes, significantly so. This is a major practical win. Figure 5 shows early fusion uses less memory and trains faster for the same compute budget compared to late fusion.
Less memory and faster training. Why is that?
Well, think about late fusion. For the same compute, it often has more total parameters because you're adding up the vision part and the language part.
Yeah.
And it's effectively deeper because the data goes through separate stacks before meeting. Early fusion, being more unified, just seems structurally more efficient.
And does this efficiency gap change as you scale up?
Yes. The paper suggests the advantage for early fusion actually grows as the compute budget increases. So for really large-scale training, the benefit becomes even more pronounced.
Okay, efficiency is a clear win for early fusion. Now let's talk about the data itself. Training these things needs images, text, sometimes mixed together. Does the mixture of data types change these scaling laws?
Absolutely. That's another key area they investigated. They tried different recipes, varying ratios of image caption pairs, interleaved documents where image and text are mixed throughout, and just text-only data.
What kind of mixes did they try?
Things like 45% image caption, 45% interleave, 10% text, or maybe more text, like 30, 30, 40. Various combinations, detailed in Table 2.
And did the scaling laws change much depending on that mix? Figure 4 and Table 4 cover this?
Yeah, the overall shape of the scaling laws was similar, but the specific coefficients, the A and B constants in that L plus and alpha plus beta beta formula did change.
How did they change? Any pattern?
Well, one interesting finding was when they increased the proportion of image caption data, the A coefficient tended to go down, but the B coefficient went up.
Okay, what does that imply practically? Lower A, higher B?
It suggests that if your data is very heavy on image captions, you might get more bang for your buck by training longer, more data related to beta and B, rather than just making the model bigger related to alpha and A.
Interesting. And the opposite if you have more text or interleaved data.
Exactly. With more interleaved and text data, the trend reversed, suggesting model size might become relatively more important in those cases.
So the optimal scaling strategy isn't one size fits all. It depends on your data diet.
Seems that way.
Yeah.
And comparing early and late fusion on these different diets.
Yeah, did one handle certain mixes better?
Figures 6 and 15 suggest that for a given model size, early fusion performed better when the mix contained more interleaved documents and text-only data.
Why might that be?
The thinking is maybe that early interaction in the architecture is just better suited for handling those more complex formats where text and image are deeply intertwined. They also mentioned seeing some interference effects between data types in the appendix, which is another layer of complexity.
Right, data composition matters a lot. Okay, another angle they looked at, starting from scratch versus starting from a pre-trained language model.
They compared their native early fusion models, trained from random weights, against models initialized with a pre-trained LLM, specifically DCLM1B, and then fine-tuned on multimodal data. Figure 8 and 20 show this.
Does that pre-training give a permanent edge? Or can the native models catch up?
Pre-training definitely gives a head start. The initialized models perform better early on in the multimodal training phase, but the native models can close the gap if you train them long enough on the multimodal data.
How long is long enough?
Well, it depends on the data again. For image captioning data, they estimated maybe less than 100 billion multimodal tokens were needed for the native model to catch up.
Okay, that's a lot, but maybe feasible.
But for data mixes with more interleaved and text content, catching up took way longer, potentially up to 1 trillion tokens.
Wow, 1 trillion tokens, that's huge. So the cost benefit of using a pre-trained LLM really depends on how much multimodal data you have and how much that initial LLM pre-training cost you in the first place.
Exactly. It's not a clear-cut win. Either way, you have to factor in the total compute from start to finish.
Makes sense. Okay, we've hit early versus late scaling, data mixes, pre-training. Now for something really cool. Sparsity and mixture of experts, MoEs. Why bring MoEs into this?
But the motivation is pretty intuitive, right? Multimodal data is diverse visual stuff, language stuff. Asking one dense set of parameters to handle everything equally well might be inefficient.
Right. Maybe some parts of the network should specialize.
Precisely. MoEs offer a way to have a huge total model capacity, but only use a small fraction of it for any given input token. You have different expert subnetworks, and the idea is they can learn to specialize.
Like having a team of specialists instead of one generalist.
Kinda, yeah. Some experts might get good at processing visual features, others at language nuances, maybe some at combining them.
How did they actually build the MoEs into their early fusion model?
They used a specific setup called dropless Moe, which helps avoid losing tokens during routing. It had 8 experts per MoE layer and used hop 1 routing.
Meaning each input token gets sent to just one expert.
Yes, the one the router thinks is most suitable. And they added a load balancing loss to encourage using all the experts somewhat evenly.
And crucially, how did they count the compute FLOPs for these MoE models?
They only counted the FLOPs for the active parameters, the ones actually used during the forward pass, for a given token. This reflects the actual cost at inference time.
Okay. So did adding MoEs actually help performance?
Oh yeah, significantly. Figure 9 shows the sparse Moe models clearly outperform dense models that had the same inference cost, same number of active parameters.
Better performance for the same inference budget. That's exactly what you want from sparsity.
And the benefit was even more pronounced for smaller models, suggesting MoEs are a great way to boost capability when your overall parameter count is limited.
What about the scaling laws for these sparse Moe models? Did they scale differently? Figure 10?
The scaling exponent with compute was very similar, around magnus 0.047, close to the dense models, but the overall constant was lower.
Meaning they just achieve a better loss level across the board for the same compute.
Basically, yes. Though they did note that Moe models seem to need a bit longer training to fully converge and reach that potential.
And the balance between scaling parameters, alpha, and data, beta, did that change with MoEs?
It did, quite dramatically actually. Table 3 shows alpha shot up to around 0.710 for the sparse models.
Whoa, much higher than the dense models 0.301.
Yeah, and the B coefficient was also higher than A. This strongly suggests that for Moe models, scaling up the training data becomes even more important relative to scaling the number of active parameters. You need to feed them lots of data.
That's a super important insight for training these sparse giants. Now, within the MoE, how does the model decide which expert gets which token? They looked at modality-aware versus modality-agnostic routing.
Right. Modality-aware routing means you explicitly tell the router, okay, this is an image token, send it to one of these image experts. This is text, send it to a text expert. Predefined rules.
Makes sense. And modality-agnostic.
That means the router just learns on its own. It looks at the token's features and decides which of the available experts is best, without being explicitly told whether it's image or text originally.
So which way worked better? Letting the model figure it out or giving it hints?
Letting the model figure it out. Figure 11 shows modality-agnostic routing was consistently better on both image caption and interleave data.
Huh. So the model learns better specializations than we can hardcode.
It seems so. The learned routing finds more effective ways to use the experts than just simple modality separation.
And did they actually see specialization happening in the agnostic case? Like, did some experts end up focusing on images anyway?
They absolutely did. They analyzed where tokens ended up, Figure 13, and even calculated a specialization score, Figure 12.
Well, what did that show?
Clear evidence of modality specialization, especially in the very first few layers and the very last few layers. The experts there tended to handle mostly image or mostly text.
But not in the middle layers.
Less specialization in the middle. The thinking is those middle layers are maybe handling more cross-modal stuff, integrating the information. But early on, you process specifics, and late, you generate specifics.
And crucially, the agnostic router could also create experts that handled both image and text tokens if that was useful.
Exactly. Something a strict modality-aware router couldn't do. It allows for more flexible sharing and specialization.
Really powerful stuff. Okay, almost there. Did they check if all this pre-training goodness actually translates to downstream tasks?
Briefly, yes. They did some supervised fine-tuning, SFT, on the LIV dataset, which involves following visual instructions. Table 7 has the results.
And did the rankings hold up? Early, late, Moe dense?
They did. The relative performance trends matched what they saw in pre-training validation loss. Early fusion generally beat late fusion, and Moe models beat dense ones.
Even if the absolute scores weren't state-of-the-art due to model size?
Right. The scores themselves were okay, not groundbreaking, probably because the base models were huge and the fine-tuning was limited. But the relative comparison held, which validates the pre-training findings somewhat.
Good sanity check. So, placing this paper in the wider field, where does it fit?
Well, like we said, most big multimodal models out there now are late fusion, often using pre-trained parts. Native models, especially early fusion, trained from scratch on raw inputs and interleave data, are less common, mainly because they're compute hungry.
And scaling laws for this specific type of model hadn't really been studied in depth?
Not comprehensively, no. Lots on LLMs starting in other areas, but this deep dive into native multimodal scaling, especially early fusion and MoEs, is pretty novel.
So it fills a real gap in understanding how to build these kinds of models efficiently. Of course, no paper is perfect. What limitations did they mention?
They were good about listing them. Needing more work on data mixture scaling laws to get a more unified theory. The question of how well pre-training loss predicts performance on all kinds of downstream tasks.
Standard caveats.
Yeah. Also, the uncertainty of extrapolating these laws to truly massive scales. Potential issues handling super high-res images with early Fusion's patching approach. And they acknowledge they only explored one specific MoE setup. Some more architectural tweaks could help.
All fair points. Good areas for follow-up work. Okay, let's wrap this deep dive up. Can you recap the absolute key takeaways for us?
Sure. 1. No inherent performance win for late Fusion over early Fusion in native models. Early Fusion is more efficient, often better at smaller scales. 2. Native multimodal models follow scaling laws similar to LLMs. Predictable improvement with scale. 3. Optimal late Fusion seems to need more parameters. Optimal early Fusion might benefit relatively more from data.
4.
Sparsity via MoEs significantly boosts early Fusion performance for the same inference cost and leads to learned modality specialization.
And 5.
For these sparse MoE models, letting the model learn how to route tokens, modality agnostic, works better than telling it based on modality type.
Awesome summary. Really fundamental findings here. So the provocative thought to leave our listeners with. Given all this, maybe the community's strong focus on late Fusion built from pre-trained parts, maybe that needs rethinking. Could native early Fusion models, especially supercharged with MoEs, be the more promising path forward for truly general AI that understands multiple senses deeply?
It's a compelling question, right? Does this research point towards a shift in how we should be scaling multimodal AI? What new architectures might emerge if we lean into native early Fusion sparse designs?
Definitely food for thought. We really encourage everyone interested to check out the paper itself, look at the figures we mentioned, and think about how this applies to your own work.
Yeah, dive in, explore the references. Let us know what you think the implications are for the future of multimodal AI.
Great stuff. That brings us to the end of this deep dive. Thanks for joining us.
Thanks, everyone. See you next time.